Okay, this is the Functional Flows Calculator Technical Overview webinar. I'm Belize Lane and also presenting with Noelle Patterson from UC Davis. So let's jump right in. California has complex natural hydrology. If we peel away all of the layers of management and reservoirs and water conveyance infrastructure, what we can see is this map here, which shows complex variable hydrology driven by variable climate, topography, geology, and soils. So our technical team previously developed a hydrologic classification for the state that consists of 9 natural stream classes, ranging from snowmelt-dominated streams here in the Sierra Nevada, winter storm streams that dominate the North Coast Range, groundwater streams here in the northern Sacramento Basin, and flashy ephemeral streams in pink here in Southern California. And you can get more details on this classification at this link shown below. So in addition to this immense spatial variability, each of these stream classes has distinct daily, seasonal, and interannual stream flow patterns. So you can see the clear snowmelt signature here, where you have these low base flows, and then this one clear spring snowmelt pulse and subsequent recession. Compared to the winter storms, we have high interannual variability, and the massive flow occurs here in the middle of winter, or low volume snowmelt and rain that shows a combination of these big winter storm events and the spring snowmelt signature. So these natural flow regimes that I just showed you depicted in these plots act as a primary control on ecological functioning, controlling many of the physical and ecological processes that the native species of California are adapted to. Flow metrics are often used to link key aspects of that natural or altered hydrology to observed ecological response in order to inform environmental water management efforts. And many flow metrics have been proposed for this purpose in the past few decades. You have the Indicators of Hydrologic Alteration, IHA, the Hydrologic Index tool developed by USGS with their eFlowStats toolkit, and then many different statistically significant subsets of flow metrics based on different ecological or management objectives. So particularly in large complex hydroscapes like we have in California, the appropriate selection of metrics remains a major challenge due to the redundancy in the set of metrics that you have, limited statistical power, and then limited ecological relevance of those metrics. So to address those limitations, instead of these empirical methods, our technical team is proposing the use of ecological theory as the foundation for selecting flow metrics based on the functional flows approach. So functional flow components refer to these discrete aspects of the natural flow regime that are expected to support key ecosystem functions. And 4 functional flow components, these boxes that you're seeing here, were previously identified as broadly ecologically relevant in California across natural stream classes and water year types. So I'm going to walk through these quickly. You have the wet season initiation flow event. This is that first flow event following the dry season that flushes the channel, kickstarts nutrient cycling, and can cue upstream migration of native species. And we have these peak magnitude flows. These are the large physical disturbance events that serve to reconnect floodplain habitat, mobilize sediment in the channel, prevent riparian vegetation encroachment. And then subsequently, we have the spring recession from our winter high flows. And this is that predictable transition from high to low flows that provides distinctive annual cues for many native species for reproduction and movement. And finally, the dry season low flows functional flow component, which constrains the extent and quality of physical habitat through the dry season and preferentially supports native species that have adaptive life history strategies to withstand these stressful conditions. So the conceptual model for the functional flows approach is as follows. Functional flow components are described using a set of flow characteristics, which in turn are quantified using discrete numeric flow metrics. So, for example, a functional flow component would be the spring snowmelt recession. And this can be described using a set of characteristics. This is magnitude, timing, duration, frequency, and rate of change. And specifically, some subset of those characteristics will be relevant for each of these functional flow components, as represented by the X's in this table. And then discrete flow metrics. So for instance, we could describe the rate of change based on the % daily flow decrease. So based on this conceptual model, we proposed a suite of functional flow metrics describing ecologically relevant characteristics of each of these 4 functional flow components for California streams. And the result is 31 functional flow metrics that are listed here in the table. And these were each calculated for 223 reference gauges in California over each reference water year in the gauge record, anywhere from 10 to 60 years in each of those records. So that's over 7,000 total water years that we calculated this set of functional flow metrics for. So we'll be talking about some of these metrics next, but the full description is available here at the bottom of the page through the Functional Flows Calculator website. And before we dive into the calculations, I just want to show how these metrics fit within CEF, the California Environmental Flows Framework. So within Tier 1, the Functional Flows Calculator, the FFC, is used to calculate these proposed metrics for all of the reference gauges in the state of California. And then the natural ranges of each of these metrics will be predicted for all of the stream segments in California. And that modeling effort will be described in a subsequent webinar. So the results of what we're talking about today, which is here in this red box, will be once we predict those metrics at other locations, we'll have a statewide map where you can click on any segment and pull up the predicted natural ranges of each of the metrics across different water year types. And with that, I'll pass it off to Noelle.
All right, here it is. So I'll now explain generally how we calculate these functional flow metrics. The foundation for all the functional flow metrics is the timing of the 4 functional flow components that we just described, shown here on the hydrograph. For example, to calculate the magnitude of the wet season base flow, we need to know first where the wet season starts and where the wet season ends in each water year. So let's move on and start with the wet season initiation event. Okay, the wet season initiation is described as the first significant peak in flow following the dry season low flows. It typically occurs each year as an early season storm flow, but may not occur in all water years. 3 metrics are used to characterize the wet season initiation. These are the timing, the magnitude, and the duration. The timing is constrained to the first 2.5 months of the water year, from October 1st to December 15th. And once this timing is set, then the magnitude and duration can then be calculated. All right, the next functional flow component are the peak magnitude flows, and these are described as the high magnitude flow events that occur during the wet season. A suite of metrics are calculated for flows that exceed the 2nd, the 5th, the 10th, and the 20th flow exceedance thresholds over the period of record, as shown in the diagram. For each flow event that exceeds a high flow threshold, the following metrics are calculated: high flow timing, magnitude, duration, and frequency. Moving on, There are two other peak magnitude season metrics that are calculated in addition to the high flow characterization. The first of these is wet season start timing, which is defined as the first state that sufficient base flow has accrued based on a flow threshold, which is 30% of the difference between base flow and peak season flow of the smoothed data, as shown in the diagram. The reason we use these relative magnitudes based on percentages is so that these metrics will work across a variety of streams and water year types of varying flow magnitudes. The second metric is the wet season base flow magnitude, and this is the 10th percentile daily flow from the start of the wet season to the start of the dry season. Okay, our next flow component are the spring recession flows, which is defined as the seasonal transition from wet season high flows to dry season low flows. Metrics calculated include the timing and magnitude of the start of the recession, the duration of the recession period, and the flow rate of change over that period. The rate of change is calculated as the median of the daily rate of change of only the days with negative rate of change. So any upward spikes of flow in that period are not factored into this metric. Later in the presentation, we'll give a more detailed view into how that spring recession is calculated for the timing. But moving on, we have the dry season low flow component, which is represented as the low flow or the low magnitude, low variability portion of the water year between wet seasons. The timing of the dry season is identified as the first date after the spring recession start that flow magnitude has lowered below 12.5% of the difference between the wet season's peak flow and the base flow of the smoothed data, as shown in the diagram. Also calculated is the low flow magnitude, which is the 10th percentile of daily flow from the start of the dry season to the start of the wet season, and the low flow duration, which is calculated as the number of days between the dry season and the wet season, and the number of no flow days, which is the number of days during this same period in which the flow magnitude is 0. All right, moving on, we have two more metrics that are annual metrics. So these are not falling within a seasonal flow component. The first of these is the average annual daily flow, and the second is the coefficient of variation, which is the standard deviation of daily flow divided by average annual flow. All right, next we'll be taking a look under the hood of the functional flow calculator at how we calculate the metric for the spring recession timing. So I'll pass it back off to Belle for this one.
Okay, so why didn't we just draw from existing metrics from IHA or eFlowstats to characterize these functional flow components? Well, these existing suites of metrics generally hard code calendar months to assess timing. For instance, we'll calculate the mean July flow or the maximum flow occurring in January. However, in as complex a hydroscape as we have in California, we really needed a method that allowed the data to speak for itself without hard coding where possible, in order to better capture the full range of natural variability that we're seeing in our stream flow. So to accomplish this, we're drawing on signal processing techniques that allow the distinct hydrologic patterns to be directly evaluated at different frequencies of interest. So specifically, we're using a combination of 3 tools: smoothing, feature detection, and windowing. So here we can see, for example, the raw stream flow data in blue underlined here. And smoothing is this process of pulling out particular frequencies of interest that we want to look at. So in this case, we're seeing the low flow period and the wet season high flow period, and not much else. Feature detections, where we can zoom into a particular feature of interest. In this case, we're looking at the peak of that smooth wet season. And then windowing, where we zoom in around that particular feature of interest, in this case represented by these yellow lines. So let's walk through an application of these signal processing techniques to calculating the spring recession start timing. So the first step was to plot the daily raw streamflow data by water year, which is what you're seeing here. Then we smoothed that data, in this case using a Gaussian filter, so that's this orange curve that you're seeing. The third step was to identify the last major peak, which represents the center of mass of the wet season here, indicated by this arrow. Then we set a dynamic search window around that peak, specifically 20 days before and 50 days after the peak flow. And now we're going to zoom in to this window for subsequent steps. So step 5 was to apply a tighter smoothing curve within that window. So that's this black smoothing curve that is much closer reflection of the raw streamflow data. And then calculated its derivative, which is the curve you're seeing here in red. And what that allows us to do is to identify the local peaks in this black smoothed streamflow time series, which indicate where the derivative flips from positive to negative sign. So each of those peaks in our streamflow time series are identified. Step 7 is then to identify the last peak that has sufficient relative magnitude, duration, and rate of change attributes to be considered an individual storm event. So we picked that out here. And then step 8 was to set the start date of the spring recession a few days following that peak event to remove the effects of individual storm events on the calculation of the spring start timing and associated metrics. So what you're seeing here is this final spring start timing. So the results of all of these efforts, again, was these 31 annual functional flow metrics that we calculated for all 223 reference gauges available in California. So the next question is, how can we access these metrics and calculate them for other gauges or years that we're interested in? So Noelle is going to take us on a tour of the Functional Flows Calculator website.
All right, thank you, Belle. So now we're attempting the live demonstration of the website. So I'll start by taking the screen here. Okay. Let's open up a new window and enter the website eflows.ucdavis.edu. Hopefully the internet connection is with us. There we go. So here we are at the landing page for the eFlows website, and we have 2 links here. The first is to go into the hydrology portion of the website, which is where we'll be looking today. And the second is this how does it work link, which is where we have documentation on the eFlows website and the functional flow metrics, and we'll take a look into that later. So let's start by exploring the hydrology. Here in the hydrology portion of the website, we have 2 main windows. The first here on the left is a map of California with a stream network showing the 9 hydrologic classes and all 223 reference gauges. So we can toggle these stream networks on and off. And if we turn all of them off, then underneath we see the location of all 223 reference gauges, and they're colored according to their hydrologic class. On the right side of the window, we have drop-down menus showing all of the reference gauges sorted by their class. So let's look into low volume snowmelt and rain, and this is where we have the most reference gauges in the state. And we're going to take a look at one in particular. I will mention you can search gauges according to their gauge ID or their name, but we're just going to scroll down to the bottom for now and look at Yuba River. Here it is, the Yuba River above Slate Creek. So what we see here is the dimensionless reference hydrograph for this particular reference gauge, the Yuba River Station. And this shows us the variability of seasons and the interannual variability in flow for this particular gauge. We have this display option up at the top, which allows us to overlay functional flow metrics on top of the reference gauge. These are, again, split by the functional flow components. So let's take a look at our metrics for wet season initiation. If I turn on the wet season initiation event timing, you see 5 vertical bars that show up over the dimensionless reference hydrograph. And these bars represent all results for wet season initiation timing across the reference water years from the 10th, the 25th, the 50th, the 75th, and the 90th percentile results for that particular metric. We can turn on the event magnitude, and that shows us 5 horizontal bars showing the same percentiles of results for wet season initiation event magnitude. And what it shows is this colored box in the bottom left of the hydrograph that essentially boxes out the functional flow component for wet season initiation and gives us the broad range within time and magnitude that this flow component occurs. Now let's close this and take a look at the annual flow plots. And this shows us the flow data sorted by water year for this particular gauge. So again, we can display the functional flow metrics over these hydrographs, and now the results will show the results of the metrics for this particular water year. So we can turn on all the timing metrics, for example, and that will give us, again, the wet season initiation event, the start of the wet season timing, the spring recession, and then the dry season low flows timing for a particular water year. And we can turn those off. We can also look at all the magnitude metrics, and this shows us a suite of peak magnitude flows and base flows across this water year. We can also do a hydrograph overlay. So this shows the dimensionless reference hydrograph behind the water year data for this particular year. And so as we scroll through, you can see how the variability from year to year compares to the dimensionless reference hydrograph, which shows an aggregate of that variability. So with all of this neat data, we might want to download it and take a closer look. And so we have an option for downloading the data up here in the top right. There are options to download the annual flow matrix that gives the raw flow data split by water year as shown in the hydrographs. And then there are metric results, which will show the metrics calculated for each water year. And we have a metrics README, which helps explain what is in this metrics result page. So I'll start by downloading this, and we can take a look. So inside this CSV file, we have all the flow metrics that we discussed in the presentation, and they're calculated across every reference water year in this gauge. And to understand what these metric names are, we also have a download for the README, which I already have open. And so this just explains what each of these functional flow metrics is, just as a quick reference. All right, back to the website. We're going to go one more time to the landing page because this is where we'll find links to the documentation. This first documentation page, here it's loading up, is an overview of the eFlows website and all the functional flow metrics, everything that's in it. So we have a description of the stream classification, the dimensionless reference hydrographs, box plots, and other visualizations, and of course the functional flow metrics. And this is where you can find a reference to more detailed descriptions of each metric, split by functional flow component. And for even more detail in the documentation, we have a link to documentation specifically for the functional flow calculator. And so this is a resource that is helpful for scientists or developers who want to take a closer look at the functional flow calculator and possibly download the repository with the Python scripts and even modify and use the functional flow calculator. So there's directions on installation of the Python scripts, and then there's more detailed descriptions of how each metric is calculated within Python with steps and code snippets as shown here. That will conclude the online overview of the eFlows website. So at this time, I will pass it back off to Belle.
Great. Thanks, Noelle. So again, we have the documentation for the functional flow metrics here at the site shown on the screen, as well as the documentation for the functional flows calculator and how to actually get into the details of the Python script here. And that's all. So thank you very much.